Hi everyone, my name is April Moreno-Ward, and today we're going to look at a comprehensive dimension reduction method analyses for channel delineation. So to start, let's look at our motivation. We want to see how we can improve the interpretability of deep water channel seismic facies and use a balance between quantitative and qualitative methods. So our question really is how we can better incorporate these machine learning techniques into our seismic interpretation workflows to both improve interpretation resolution and help increase confidence in geologic interpretation. So to orient ourselves, we are off the coast of the northern island of New Zealand. We've got our seismic data, which is our Romney 3D seismic data. We've cropped it to this pink outline here, so a smaller subset, and we do have one well. It's the Romney 1 well. And for those of you who'd like to see information on the data, here's a table. Okay, so moving forward, in terms of trying to identify seismic channel facies, we want to make sure that we have a good understanding of modern analogs. So we're looking at a satellite photo of Mississippi River, a portion of the Mississippi River. And when we look at this, we can go ahead and start picking out some of the channel geometries. So I've highlighted the old abandoned loops in blue, and then I've also highlighted where we have movement of those channels or scroll bars. So that helps us to understand the direction of movement for those channels. We also can see some of those prograding sandbars. So if we can pick out these features in modern day analogies or looking at recent past, that's going to help us ensure that what we're looking at in seismic data has a good reference point. The next consideration that we really need to have is the idea of perspective. So when we look here, we've got a horizon that's been picked on our unconformity that our channel cuts into. Looking at it from just a map view or that horizon view, we can see that we do have a channel that has a little bit of sinuosity to it. And we might misinterpret this as being a single channel if we're not careful to think about the scale. When we look at it in terms of adding in our inline and crossline and really starting to think about the actual scale of the feature, we do see that indeed this is going to be a much more complex stacked channel feature, if you will. So perspective is going to be important when we're looking at interpretation. Looking at the data we already have, we've got the well logs from our Romney data, and then we also do have our seismic. We can go ahead and start to identify different facies that we have. So that's what we've done here. We've taken our well log data, we've picked out some very easy to see benches in the well logs here, and we've gone ahead and we've picked out 5 different well log facies. We well tie, look at what our seismic response looks like, and so we can go ahead and have an understanding of what those lithologic facies actually look like in terms of the seismic response. However, quick reminder, our well location is not within the channel that we're actually trying to identify. It's about 8 kilometers away. So that means we're going to have to take those facies that we've picked out and we have to interpolate them into the channel of interest. And so we can go ahead and pick out some of those similar seismic responses. And while we don't know with data truthing whether those lithologies that we see in the well log will be the same as what we see in the channel, we can at least have a good idea of where we're going to see coarser grain material and finer grain material. Using our background knowledge that we have in channels, we can go ahead and see if where we've identified coarser grain material makes sense with where we understand it to be in terms of channel morphology. Okay, so now that we've gone through, we've looked at the information that we have, we want to go ahead and start bringing in that next step, thinking about the machine learning part. But where do we start when we have all of this data to start looking at? So initially, we've got our data. So we've got to figure out what attributes we want to look at in our seismic. Then if we're going to bring in the machine learning aspect, we need to figure out what type of machine learning technique we want to use. And for us, we're focused on dimension reduction and clustering as well. So which of those dimension reduction techniques are going to be appropriate for what we're doing? And then as we're evaluating each of these dimension reduction techniques, we also have to figure out what type of scoring we're going to use when we're determining which algorithm is actually performing best. And then once we do that, we start to evaluate our clustering. Well, now we need to figure out which clustering is going to be most helpful. So is k-means the best clustering algorithm to use? How many clusters is actually performing the best? And then in that analyses, are we looking at quantitative analyses? Are we looking at qualitative? Or are we finding a way to balance both of those? And then, even after we do that, we've got to start thinking about our visualizations. So, are we looking at histograms or graphs to help us determine which model is going to be best? Do we need to focus only on the clustered models at the end? How are we trying to get that geologic insight, right? It's a question that we might have. That's a lot of information to take in. But at the end of all this, what we want to do is find a way to weigh the value of information that we're acquiring to help us make decisions. Because we don't want to find ourselves in a position where we don't really understand all of this input information. We're just kind of maybe putting it all in a cup and maybe rolling the dice and saying, well, whatever comes out of this is going to be good enough. I'll go ahead and interpret it. That's not where we want to be. Where we really want to be is having an understanding, at least a fundamental understanding of what's going on in each step of the way, because we do want to help make sure that we're improving the resolution of the data to help us improve our interpretability. And we want to make sure that we are improving the confidence when we're presenting these interpretations. And so this is what I'm doing in my PhD project. So essentially, this is all three of the chapters that I'm working on here. Okay, so moving forward, my workflow. So we're initially starting with making sure that we're pre-processing the data. We're defining the AOI, we're picking out the attributes that we have identified are going to help us delineate channel features best. We're making sure that we're doing our well tie, and then of course looking at the lithology and facies identification. Chapter 1 we have sent off for publication. It's currently in review. That's where we have identified each of our dimension reduction algorithms, and we've gone ahead and we have tested those to see which allows us to better delineate internal channel architectural elements and which ones perform best in terms of a map view or that horizon view. And where we are right now is our chapter 2. This brings us to our clustering analyses and interpretation. So we're looking at verifying each of our clustered models using various metrics, and then we're also comparing our pre-dimension reduction and our post-dimension reduction, making sure that we're looking at both our qualitative and quantitative evaluations when we do this. Attribute selection is going to be one of our most important first steps along with algorithm selection. But when we look at which attribute we want to use, we want to make sure that we're using those that are going to help us identify channel features best, whether it's identifying channel edges, telling us something about grain size within the channel, helps us to determine channel migration, flow direction. And so we can look at each of these attributes and go ahead and start to interpret some of those key features. Of course, not each of these attributes is going to help us identify all of these channel morphologies equally. And so that's where we might want to go ahead and start co-rendering these attributes. However, we are only going to be able to co-render so many of these attributes before it really starts to actually make the resolution worse and make it harder for us to be able to pick out some of those key features. And so that's where the dimension reduction becomes important in our workflow. But when we look at all of these different algorithms, there are quite a few, and so it becomes a little bit difficult to figure out which ones are actually going to be most helpful. So, looking at various different algorithms, we kind of landed on k-means right now to do our unsupervised clustering, and ICA and PCA, which are two that have already been used in seismic workflow. So that's going to be our baseline. And then we're bringing in our kernel PCA and our UMAP as kind of our novel dimension reduction techniques that we're testing. And then within each of those dimension reduction techniques, we also really need to understand what is being measured, how those attributes are being weighted in terms of how they're affecting the dimension reduction, to make sure that when we're looking at those outputs, again, we've got a baseline of knowledge to ensure that what we're evaluating as a top performer is actually a top performer. When we take those metrics though, and we start to really try to think about the number of clusters that's going to be better, there are also still a lot of considerations. So we might maybe start looking at each cluster and think, well, if we look at the distance to the centroid, look at that mean distance, maybe that's going to be the way that we evaluate number of clusters. Or we could use things like the silhouette score, we could use things like the DBI score. When we're looking at these metrics, we want to make sure that we're keeping in mind that it's not the highest number of clusters that's necessarily going to be best. We want to find a way to balance intra and inter cluster performance when we're looking at our best number of clusters. But before we even really get to that part, we might have this question, which I hope each one of us does, which is, okay, if we're looking at dimension reduction to help us improve resolution, what does the resolution of these techniques actually look like before we even start to look at clustering? And so we've done this. We've taken our ICA and PCA, which have been reduced from those 6 dimensions or those 6 input attributes down to 2 dimensions and 3 dimensions. And we're trying to, again, pick out those internal channel features. Compare those to our novel techniques, so our KPCA and our UMAP, and really start to see which of these techniques does improve resolution to allow us to see those internal features. And here's a few of our attributes for comparison. So where we're looking at this, we've determined that KPCA is going to be the dimension reduction technique that's actually improving resolution for those internal features best. Okay, so moving on to our quantitative evaluation then. We're testing unsupervised clustering, so we want to look at it before we've done any of the dimension reduction. So initially, we're going to take our input attributes, put it into k-means, evaluate our silhouette score and our elbow method, and then what we've seen is that those clusters tend to be non-unique. We've got a lot of data overlap. And so then we bring in our dimension reduction, taking our same 6 inputs, looking at our dimension reduction techniques. Then we're looking at performance and we're looking at attribute weights, taking that, putting into our clustering now, reevaluate again for our silhouette score, elbow method, and then looking at overall cluster performance. Quantitative, our top 10 performers are listed here. So 9 of the top 10 performers, total we have about 55 models that we've looked at. KPCA takes the top 9 spots. When I look at each of these cluster graphs though, I don't really see initially a whole lot of difference. I can maybe start seeing where I've got some separation between these clusters, but in terms of being able to evaluate data spacing, it's going to be very difficult for me to do that. But if I compare the post-DR clustering, which is here, with the pre-DR clustering, I can definitely see that there is a significant improvement in terms of spacing, data overlap here. If I start to look at the statistical metrics, we can start actually looking at the values we're getting back for the silhouette and DBI score. Focused again on those top 10 performers, I'll see that I do have my kernel PCA. I also have kernel PCA with optimized hyperparameters. But for those first 9 instances, the optimized parameters haven't really improved overall performance. So if I go ahead and redo my table, taking out those optimized hyperparameters, what I see is my UMAP is moving in to the top 10 scores. Not a lot of difference initially from our silhouette score here, but getting down to the bottom, we start looking at some of those lower performers and we do see a significant increase in performance. From a qualitative perspective, when I'm looking at intra and inter-cluster spacing, these are the ones that I perceive to be the top 10 performers. It's easy for me to see good separation between clusters. There's not a lot of spread between these initial ones, okay? But again, if I were to go through and try to measure each data point to start looking at spacing, I'm no longer improving that calculation time. That's going to take me significant effort to try to figure out and weight that data. The other thing that I need to be mindful of is thinking back to the perspective that I mentioned earlier. So dimensional perspective is going to be very important. If I take each of my cluster models, and especially where I've got 3 dimensions or those 3 components, instead of just evaluating it in 2 dimensions, I've got to remember that I've got 3 dimensions there. So if I take each model, put it into 3 dimensions, and really start to rotate through, my perspective of data overlap is going to change significantly. And so while many people might hear me say that and think, well, yeah, of course you have to consider the perspective. For a new user, there's so much information we're trying to evaluate, so much information we're trying to learn, that a step like dimensional perspective might be something that's overlooked quickly. So here's my reminder to really have all of us think about looking at the data in multiple dimensions when we're evaluating that. Okay, so our next step, or our chapter 3, is going to take each of those unsupervised clustered models out and put them into software where we can actually geologically render those. We need to evaluate each cluster that has been picked out, apply meaning to it. Are we looking at channel edges? Do we have coarser grained material? Do we see improvement in the actual geologic model compared to what we were looking at in terms of the statistical evaluation? So this will be our step 3. Hopefully I'll have this finished by spring of next year. And so to kind of wrap this up, here are my key takeaways. When we're looking at seismic geomorphological interpretation, it is going to be very dependent on our data resolution. As a human interpreter, the better the resolution, the easier it's going to be for us to be able to delineate some of those subtle features. We can improve seismic resolution. We can improve seismic resolution through making sure that we have the proper selection of analyses tools. Machine learning is going to allow us to be able to evaluate multiple attributes at the same time, and it's also going to help increase the speed for quantitative evaluation. However, we want to make sure that we're not just becoming dependent on what the statistics are telling us. We need to make sure that we're also balancing it with the quantitative evaluation, make sure that we're putting eyes on the data as well. So a big thank you to everybody who's helped me get this far in my research and to all of our Ask Bee sponsors. I hope you guys have a good day.